Okay, so in this video we're talking about the area between two curves. So if we have two curves on your graph, maybe like a quadratic or so, and I don't know, a linear one or something like this. Okay, so we need to know a couple of things, right, in order to find the area between these two curves, right? This is what we're looking for. How much area is there between those two things? So the first thing we need to do is find the lower bound, right? Where do we start? And then find the upper bound, right? Where do these things intersect? So usually when you're trying to figure out where two functions intersect, you set them equal to each other and you solve for x, which is exactly what we're going to do here eventually, but not at the very moment. So then we find the area between these two curves by taking the integral from your lower bound to your upper bound of your top function, okay, and in this case the linear function, because literally it is on top, it is above, minus the function that is below. So it's the top function minus the bottom function. Okay, and of course this is d whatever, dt, dx, dy, dz, d something. Okay, so we're going to be trying to figure out what function is on top and what function is on bottom, and what those points of intersection are for a couple of different functions. Now on our paper, of course, we have a bunch of them that are graphed for us, so we have a space to graph them. So we'll be practicing some graphing as well as talking about how we actually find the area between these two curves. Okay, so let's start off with our first function that looks like this. So let's look at this sketch of this real quick. So we'll do the x plus 1 in yellow, and we'll do the x over 2 in green. Okay, so we have your y-axis and your x-axis. The x plus 1 crosses the y-axis at positive 1, and it has a positive 1 slope. So 1 up, 1 over, 1 up, 1 over, 1 up, 1 over, right? So this is the graph of x plus 1. If I had tick marks on there, you could see the rise over the run as 1 up and 1 over. Now for this one, this is the graph of half of x, right? X over 2 is the same as 1/2 of x, which means we have a y-intercept of 0 and a slope of 1/2. So 1 up, 2 over. So this is the graph of x over 2, or half of x. Now our bounds, we have a lower bound of 0, so we're going to put in our left fence here at 0, and we have an upper bound of 4, so we have 1, 2, 3, 4. This is our upper bound. Okay, so when we take this integral, we're going to find this much, the area between these two curves. Okay, bounded by 0 on the left and 4 on the right. Okay, so let's do the work then. What is the antiderivative of x plus 1? X squared over 2, right? We add 1 to the power, and we divide by that power, plus the antiderivative of 1 is just x minus the antiderivative of half of x is once again x squared divided by 2. So half times a half is a quarter. So this is x squared over 4, and we're evaluating this from 4 to 0 or from 0 to 4. Okay, so let's evaluate by plugging 4 into all of your x's and simplifying. So let's see what we get. 8. We get 8. When you plug in 4 and you do the math, you get to have an area between your curves of 8 square units. Okay, so it's important to be able to sketch these so you can see which one is on top of the other, so that you do the top minus the bottom correctly. Okay, let's look at another maybe more challenging one. So here's a nice trig one. We have the interval from negative pi over 4 to positive pi over 4 of secant squared x minus cosine. Okay, so according to our formula, the secant will be the one above because it's the top minus the bottom, and the cosine will be the one below. Okay, so just do a little sketch real quick. See if you can remember how to sketch these graphs. Okay, so cosine might be easier. Cosine starts at a maximum and has a 0 at pi over 2, right? So cosine will go down like this, and also to the left, negative pi over 2. Okay, now this is more than our interval, right? Our interval just goes from negative pi over 4 to pi over 4. But this is kind of what the graph of cosine would look like, right? It will, of course, go down to a minimum and then come back up to a max. And that would be 2 pi. It takes cosine 2 pi to do a full cycle. Okay, so then the secant is the inverse of the cosine. So wherever cosine is 0, secant has an asymptote. Okay, so the secant graph looks sort of parabolic in nature because that's what the inverse of the bottom curve is. Okay, so the inverse of the reciprocal of a bottom curve is a top parabolic curve. Okay, so this is sort of what it looks like. We're going to go from negative pi over 4, which is halfway, right? So which is about here, to positive pi over 4, which is about there. So we're going to be finding the area between these two curves, which is this little section in between here. Okay, so sometimes being able to see what we're finding is important. Other times it doesn't really matter one way or the other. But just to review some pre-cal, here's the graph of secant squared and the graph of cosine. Okay, but let's get into the calculus. So let's take the antiderivative. So what is the antiderivative of secant squared? It's just the tangent. And what's the antiderivative of cosine? Well, that's just the sine. Okay, sine's derivative is cosine, so cosine's antiderivative is sine. And we're evaluating this from pi over 4 to negative pi over 4. Okay, so if you have a unit circle handy, or if you've memorized it, would be even better, because we need to find what the tangent at pi over 4 is, minus the sine at pi over 4, minus the tan at negative pi over 4, minus the sine at negative pi over 4. Okay, so having a unit circle memorized is fantastic for the test, but of course if you're just in class, then you can have access to all of this stuff. So let's talk about what is the tangent at pi over 4. Hopefully you know that is positive 1. Okay, and the sine at pi over 4, hopefully you know, is root 2 over 2. Okay, so we have 1 minus root 2 over 2. And then minus the tangent at negative pi over 4. So negative pi over 4 is in the fourth quadrant, the same as positive 7 pi over 4. So the tan down here at negative pi over 4 is negative 1. And the sine at negative pi over 4 is negative root 2 over 2. Okay, so we have all of this in here together. So let's do some subtractions, shall we? Yes, we shall. So I have 1 minus negative 1, which is the same as 1 plus 1, which is 2. Okay, and then I have negative root 2 over 2 minus a positive root 2 over 2. So I have negative root 2 over 2 minus root 2 over 2, which is how much? Well, that's just negative 1 whole entire root 2 over 2. So your answer is going to be 2 minus root 2 for the area between these two curves. So let's change it up a little bit and look at what happens when we have a y function type of an equation. Okay, so here we have a couple of y functions, right? We have a 2 minus y, linear type y function. We have a minus y squared, which is a quadratic type y function. And of course it is dy. That's the variable we're taking the derivative with respect to, the anti. Okay, so remember it's the top equation minus the bottom equation. Okay, but that only works for x's. So if we're talking about y values, okay, we have a y function, then it's the positive one, or usually it's the top, but positive in the y direction is the right side. Okay, so this is the rightmost equation minus the leftmost equation. Okay, that's the way it works if you have a y function. If we have x functions, then it's top minus bottom, right? Because top is positive and bottom is less than, so top minus bottom. But if we're talking about y's, then we have the right equation minus the left equation, or the right graph minus the left graph. Okay, and then these become y intervals. Okay, the y intervals. So let's take a second and sketch, and maybe we can make some sense of this. Okay, so here's our graph. We have 2 minus y. Okay, so maybe we should change that into an x to make it more. So x equals 2 minus y. So if we solve this for y, we get negative x plus 2 is equal to y. Okay, so that has a y-intercept of positive 2 and a negative 1 slope. So let's see, I'm doing this one in green. So here is the graph of x equals 2 minus y. Let's see if that's true. When y is 0, x is 2. So we have 2 comma 0. And when y is 2, x is 0, right? So we have, this is the graph that corresponds with negative x plus 2 equals y, or x equals 2 minus y. Okay, and then we have our other graph of x equals y squared. So x equals y squared is a parabola that opens to the right. Okay, a parabola that opens to the right. So it's the positive square root of x, and it's the negative square root of x. Okay, so if x equals y squared, then y equals plus and minus root x. So it's the top half of the roots curve, and it's the bottom half of the root curve. So notice now the area that we're trying to find is this in between here. Okay, which is why they did the y minus 2 minus the y squared. Because if you approach your graph from right to left, we run into the green graph first before we run into the yellow graph. So it's the rightmost equation minus the leftmost equation. Okay, and I said we do something with the y values, right? So we have a y interval of negative 2 to positive 1. Okay, because that's where the y values are the same, here and here. Okay, so there's two things that change when we have a y function. First, it's the rightmost function minus the leftmost function. Just like we had top minus bottom for x functions, here we have right minus left for y functions. And then we change and we look at the interval along the y-axis. Okay, so this is the interval that we're talking about from negative 2 to 1, rather than the x-axis interval that we do for normal, I say normal, but for x function integrals. Okay, so we're going to integrate this just like we do in x. Okay, there's nothing different with our y's than there is with x's. So what is the antiderivative of 2? Well, that's 2y. Right? The antiderivative of y is y squared over 2 minus the antiderivative of y squared is y cubed over 3. And we're going to evaluate this from negative 2 to 1. Okay, so we antiderive with respect to y, so all of your derivatives or antiderivatives have y's in them. Okay, but the math, quote unquote math, is done just the exact same. So we're going to plug in 1 and evaluate, and we're going to plug in -2 and evaluate. Okay, so we do all of that, plugging in and adding and subtracting, and we get 4.5. Okay, so when we have a y function, it's the right function minus the left function, and your interval comes from your y-axis, not your x-axis. Okay, so let's look at another example where we have a y as your function. Okay, so here we have the integral from 0 to 4 of 2 root y minus y. So remember, for our function, the 2 root y is going to be to the right of y. Right? So it's going to help us when we sketch this to actually know what we're trying to look for. Okay, so let's do 1, 2, 3, 4 to the right. Okay, so the easier one is probably x equals y, which is the same as y equals x, which looks like this as a graph. Okay, now 2 root y, so if y is 1, the square root of 1 is 1, 1 times 2 is 2. So when y is 1, x is 2. Okay, and of course when y is 0, x is 0. And when y is 4, the square root of 4 is 2. 2 times 2 is 4. So we have the point 44. So this is what the graph of 2 root y looks like. Okay, it's sort of like the right side of a parabola. And since it's right minus left, we're looking for the area between these curves, which is that section. And we're looking for the interval from 0 to 4, right? The interval from 0 to 4 on the y-axis. Okay, so that's a picture of what we're looking at.
The y one is just the straight line?
X equals y is the green straight line, the same as y equals x.
Okay.
X equals y is the same as y equals x. Okay, and then 2 root y looks like 1/2 of x squared, the parabola. That's kind of wide, but only the right side. So let's take the antiderivative of 2 root y. Okay, so it might be easier if you change it into a polynomial, 2y to the 1/2. Because according to our polynomial rules, we add 1 to the power and we divide by the new power. So 2y to the 3/2 divided by 3/2 minus y squared over 2. We're going to evaluate this from 0 to 4. Okay, so a little bit of algebra. We multiply by the reciprocal. So division by 3/2 is the same as multiplying by 2/3. So I have 4/3 of y to the 3/2 minus, of course, 1/2 of y squared, evaluated from 4 to 0. Okay, so this might take a little bit of brain power to know how to raise 4 to the 3/2 power. Okay, so we can do two things. We can do the square root of 4 and then cube it, or we can do 4 cubed and then square root it. Okay, either way, this value becomes 8. So 8 times 4 is 32. This becomes 32/3. Okay, and then plugging in 4 here, we have 1/2 of 4 squared. 4 squared is 16. 1/2 of 16 is 8. Okay, so it might be helpful to change this into 10 2/3. 10 2/3 minus 8 is 2 2/3. So that's going to be the area, square units, between the curves of 2 root y and y from the intervals of 0 to 4. Okay, so two things. When it's an x function, you do the top minus the bottom, and you use an x-axis interval. When it's a y function, it's right minus left as you come across the graph, and it is the y interval from a lower y value to an upper y value. Okay, and that's how we find the area between two curves.